Welcome to my talk, Mocking IoT. In the coming, let's say, 30 minutes, I will try to explain you why I think you should mock IoT devices when developing them and actually developing mobile applications for them. I know most of you are backend developers, but let's see, maybe everyone needs a change once in a while. This talk will be a story. Normally, I would say to you now that this is a purely fictional story and that all, let's say, people and events are made up. But I can't. This is actually based on my experience doing IoT projects, and so the events in there are events that I participated in. So let's first start by introducing myself. My name is Antoni. There are two facts about me that you should know. First of all, I studied information and telecommunication technology, which explains why I'm interested in all kinds of sorts of ways how devices interconnect with each other. Secondly, for the past 8 years, I was developing mobile applications in a software house in Warsaw. And now with the advent of the Internet of Things, I found myself in this perfect spot between mobile applications and embedded devices and the interconnection between them. Currently I work, or still work at Polydia, where I lead the Labs initiative, which is let's say, research and development thing. We do a lot of IoT, VR, mobile machine learning topics there to just get the foot into the newest trends. And now the question to you is, how many of you have any experience with IoT or did embedded programming at all? Raise your hands, okay, group, nice. Professional or hobby? Hobby? Okay, so yeah, that's a nice thing. I would encourage everyone to start playing with it because it's super nice, super interesting, and it's a little bit different than what we are used to. Now, let's introduce the client, John. So, John is our imaginary client, he actually represents the sum of all the clients we did with our projects. John is a manufacturer of light bulbs. I would say he is very successful. Part to his constant following of the market trends. So, for example, when the LED bulbs become reality, he was one of the first to provide a line of LED bulbs with his company. Now, recently John heard about this new fancy concept of Internet of Things. So he thought, that's exactly what I want to do. And therefore, John decided to produce and put intelligent smart bulbs to the market. Now, as always in these kind of situations, John asks his engineers to meet and to inform him or to actually gather what would be necessary to perform this task. They isolated 4 components that they need to make this happen. The first one is the bulb, of course. The second one is some embedded microprocessor that would provide the, let's say, intelligence for this bulb. Then there will be a connection protocol or technology involved. And finally, the mobile application that would control this bulb. This may be not the most, I would say, complicated solution, but it represents a big chunk of IoT projects you will find. Now, when it comes to expertise in the company, they're very good at doing bulbs, of course, and they have some experience with doing MTUs, so microcontrollers. They're actually experts in that. So the first 2 parts they can handle. The problem is actually with the second 2. They don't have any experience with mobile protocol or communication protocols. They don't have they have zero experience with mobile applications. So for John, this means he needs a partner, and that's the place where me or we enter the stage. So the product becomes a reality, and now, like always in the beginning of a project, we need to specify what we need, specify an architecture, and think about what will happen next. So this represents more or less a typical application when IoT is considered. We have a UI layer. Like on the upside, we have some layers depending on UI, connection logic, pairing with devices, and onboarding. On the other side of the wire, we have a pretty complicated function for controlling all the, like, say, things like current that drives the LEDs and over temperature conditions and stuff. And there is a very thin communication logic on the bulb side. So on the left side, there is a very thin communication logic part that puts this all this together. And in these three lower levels, we have an application protocol, which is based on a base protocol. Think something like TCP, HTTP, or more IoT protocols like MQTT, or GATT, which is a protocol for Bluetooth Low Energy. And then we have the communication technology, which actually is Ethernet, Wi-Fi, or Bluetooth Low Energy. So this set, we decided with John to split exactly where we should, as along our expertise. So John will take care of all the hardware, and our team would do the mobile application, and we would collaborate on the protocol. As you may know, time is money, and that means we need a schedule, because everyone wants to put now smart bulbs to the market, and we need to hurry up. So, like as always, managers create wonderful charts for time. This plan assumes that some time after beginning of the mobile application, we would get from John a prototype of the bulb. It will be more or less a development board, stick together with wires and doing any kinds of work. And we could already start working on it. Then after some time, we would get a second prototype, which would be more refined, maybe already have a true casing, maybe actual functions. And then after that, the prototype 3 which would be actually a release candidate. And after that, the bulb would go into pre-production, meaning they would start producing it before releasing actually to the market, because they need to have a small amount of bulbs in the beginning. In the meantime, we would develop, and somewhere after starting of pre-production and begin of sales, we would have some time to test. Sadly, reality says something different. It's a little bit different. If the prototypes 2 and 3 will get delayed, and I assure you they will, we will get into some trouble. First of all, we can, of course, develop the parts of the application that are not related to communication, but that would quickly end. Waiting for the prototype means we will have to wait, and then when the prototype 2 comes out, we will have fewer time to finish the communication, and then at some point we will get into the situation where pre-production ends. They will like to release the bulbs, and we didn't even finish the application yet. Even worse, we had less time to play with the bulb and experiment if our protocol is good enough, meaning that if somewhere in the pre-production failure we find a bug in the hardware, then they need to actually stop it and begin, and that's insanely costly. So that's the situation. Now, this basically means if the prototype 2 and prototype 3 gets delayed, or any kind of the hardware gets delayed, we will get into serious problems with the project. Yeah, managers tend to do like hectic moves right now and go through the room and not be very happy. Software engineers are, of course, better in that. We know how the solution to that's mocks. Now, a presentation wouldn't be nothing without the definition, so please, that would be it. I found it in 5 seconds on Wikipedia, and I completely agree with it. I would even highlight the, let's say, 3 most important parts of it. First of all, mock is a simulated thing, so it's not the actual bulb. It's something that mimics the behavior of the actual bulb, so it needs to have the same interface. And finally, it needs to be controlled. So we need to make sure that it always behaves like we want, and also in the ways we want it to behave. Now, most of you did unit tests, I can assume all of you. Anybody without unit test experience? Okay, good. So most of you would say, mocks, unit test, easy. Now, the mocks I am talking here about are a little bit different. They are not, mocks and unit tests are designed to wrap around a part of the code into a shell that is fully controllable, and we can separate it and have no side effects. Now, these mocks are here to replace parts of the app that we cannot develop yet because we don't have access to a hardware solution yet. So we will actually use them on running apps on mobile devices, for example, for testing of the UI and other parts, so that we don't get blocked by this missing part of the model. Of course, as always with testing and as always with mocks, there is a need for clean interfaces and a need for a good architecture that allows us actually to replace parts of the code or modules of the code with these mocking solutions. And that's something that we are used to. Now, the question is where we should mock and where we could make this cut and put a mock in it. In this layer, we have very good candidates where we could put these mocks. But what we choose is strongly, influences strongly what we will get in the end. So, of course, we could mock in the higher level communication logic. This is okay for unit tests, by the way. It's a perfect solution. But there are actually there is many code below this level that we would like to write and test and not have to wait for it. So in the context of this presentation, I would say that's too high. We could go of course, a little bit lower to the application protocol, but still, first of all, it tends to have a very huge API, so very huge interface, so that means a lot of mocking. And secondly, it's again a lot too high. Now, the base protocol, so basically functions for sending data, receiving data, streams, connecting and disconnecting from devices without actually going into any kind of understanding what it gets transferred, is the perfect place. That's normally something that you get from the system. So that's the lowest place you can actually mock, and because you have control of it over it. And on the other hand, it has a very nice small interface, so I would say that's perfect. Now, these kind of mocks, they are still running on the application. They have a basic problem. They don't simulate all the characteristics of radio communication. So jitter, delay, loss, and so on and so on. We can, of course, try to simulate it, but we will never get it right. So for the sake of, let's say, correctness of the mock, we need to cross the wire to the other side. And that's the final solution, one that I would recommend you also try, meaning that you write a small device that behaves like the actual bulb, but doesn't do any higher level functions that this device does. It only has the interface to it. We can talk to it. It actually uses the true radio communication, but it doesn't do anything else. It doesn't need to be optimal. It's plain, simple communication. So in words, if something talks like a duck, it is a duck, even if it doesn't have a body. Okay, it's only the bulb. Now, some of you may have noticed I talked about mocks and control in the when we talked about the definition of mocks. Of course, radio is not something that you can control. It's enough you have enough Bluetooth mouses in the proximity, and suddenly everything works far. Everything, the delays and the loss ratio goes to the roof. Of course, you lose a little bit of control over the radio with these mocks, but still you are simulating real-world scenarios. So this is basically what you will get. So if you want to have full control over how the high-level mock functions, so the communication works, you can stick with the base protocol mocks. And then if you want the full simulation of the radio characteristic, you need to go to the other side. So whatever you choose, you will get. Yeah. So till the end of this talk, I will talk about two approaches: this base protocol mocks, which, in my opinion, are a nice solution running on the app, and also device-driven mocks that allow full simulation of the radio characteristics. So when we think about base protocols, we typically think about three function sets. The first one is related to discovery, so finding devices that are in proximity. Second one is connection management, so basically connecting and disconnecting from these devices and maybe monitoring the state of the connection. And then the third one is data exchange, so actually transferring data. For TCP protocols, I think most of you know it better than me. We have TCP, which has basic streams of data. We have WebSockets, which transfer messages. And we have MQTT. How many of you used or heard about MQTT? One. OK, three. Good. MQTT is actually a protocol defined for the Internet of Things, or more or less defined for the Internet of Things. It scales very nicely. And the nice part is it has a small model around channels where you can, it's actually a publish-subscribe model. So you subscribe to channels, and then you can publish messages on those channels. Now, all these three protocols in the bottom have one in common. They don't think about discovering other devices. Typically for TCP-based protocols or IP-based protocols, it is assumed that someone knows the address. And that's something MDNS-SD was created for. That's a extension of DNS which allows the discovery of local devices using IP in the same network. So if you want the whole package, and for IoT you need all these three functions, you would use a mix of that. Now, there are other technologies for the Internet of Things, and mainly this is Bluetooth Low Energy. Now, in comparison to the previous ones, it has this thing that it is a full package. It has all the functions that you need. This means you can scan, and then you can connect and disconnect, and you have a model based on services, characteristics, and descriptors. So this is a three-layer model. And with these three constructs, the services, characteristics, and descriptors, you actually do the whole interface of the device. Now, in the context of mocking, these are 12 endpoints, and that's not something that we would be happy to mock, because for every invocation of any of these endpoints, or these functions, we would have to provide a mock, and that's not something we need. And that's my first tip to you: abstract a lot. So abstract everything away that you don't need. For example, in Brutal Low Energy, after connection, you have this thing of discovering which services and characteristics are available on this current device. That's not something that you need to invoke manually. You can actually abstract it away in a connector, and it will happen after connection automatically. You don't need this endpoint in the mock. So I would dare to say that this right interface is far nicer than the left one. Yeah, that's Swift, by the way. Comes with the job. These are actually 3 interfaces that we can define for this for the abstract model we had on the previous slide. We have a peripheral manager that has the function to scan and reactive RX observable for these peripherals when they get discovered. Then we have a peripheral which actually represents a device, and we can connect and disconnect to it, and which also lists characteristics that are available on this peripheral. And then we have a characteristic which actually allows us access to data. Now, remember John? Yeah. For John and his bulb, we can define very quickly a very simple service and characteristic. We will have a single control service with one light on characteristic, which will hold a single byte, which will simply say light on or light off. Of course, in a real world scenario, we would also add, for example, temperature of this bulb, or for example, something like mileage. So how much this bulb is used and how long it will last. Okay, so time for the first demo. Okay, so as promised, these are the interfaces you already saw. Now, what this application is built of? Sorry. This application is super simple. It just has 3 screens. So that's actually a controller. That's not important. We have a select bulb screen, and we have a bulb detail screen where we can control the bulb. That's it from the interface. Now, if we run it, and we can run it on a simulator, yeah, takes time. Yeah. So we have this bulb. We have a list of bulbs. Notice Mach 1. And we can, after selecting it, it will actually automatically connect, and we can change the light. Of course, nothing happens here because that's a mock. Notice that I am using the simulator. So that's again something that you gain by using these mocks. You can run on a device that doesn't have the hardware to, or a simulated device that doesn't have the hardware to actually connect to a separate device. Now, let's have a look at the mock, because that's probably the most interesting part of it. So if I have the interfaces, I can just create myself very simple classes that provide us with this functionality, or actually something. So, for example, if someone calls scan, it will generate a stream of 2 mocks, which will get sent after 0.6 seconds. So that's my simulation of a real-world scenario. And that's it. We will get a mock peripheral, which will behave mostly like a normal device. If I can then go down there, we have a little bit more code, mainly because we need to simulate everything. But again, after connecting, we will just, we'll just send on the observer for connections, we will just say connected after it is a delayed stream, so it will happen, for example, after 0.5 seconds, and so on and so on. Now, when we come to configuration, I have just this little line here that says me, okay, the peripheral manager for now should be a mock peripheral manager, and then I give it to the model. I will not show you the model because it actually wraps the peripherals and takes basic input like connect, light on, light off, and translates it into characteristic write and stuff. So that's not something that we are interested in, and the code is the same. Now, if I would like to, yeah, okay. Moment. I need to now prepare the second demo. Now I have this second mock, second peripheral manager, which actually wraps the system internal, like the system provided Bluetooth Low Energy API, and I can just run it on my device, which I will do right now. So switching to my iPhone. Okay. Now a little trick so that you can see all my screen. Yeah, so if you look at this, oh, sorry, that's not this app, that's this app. It's actually the same application. It's running on my phone, that I am not cheating. Now it doesn't detect anything because we don't have any bulbs in here, sadly. John didn't provide us one yet. So, yes. Yeah, thank you. Going back. Now, base protocol mocks are super because we can start working, we can implement them quickly, and they just work. And they work on the simulator, so that gives us already a huge opportunity, like huge advantage. But now, going back to this device, the idea of device-based mocks, we can cross over, and I would really recommend you to do this. As a reminder, this is what we are striving for. And now, when it comes to choice of technology, we have a lot of options, and we need to, again, do a little, we need to choose something depending on what we want to achieve, and depending on what we choose, we will get. We can go for easy of use, so basically simpler API, simpler hardware to work with, but then we most of the times lose some of the control. We can go for conformity, so how well this mock will mimic our device in how many aspects and how much, again, conformity comes with control. Availability, so do we want this mock to be easily available? So, for example, that our client can also buy himself one and test our applications with it. These are the main 5 functions. Then when it comes to hardware, we have a pretty nice choice. We have something to choose from. First of all, we have high-level integrated, what I call. So most of modern computers have already hardware that is capable of communicating. Mobile phones have them. The nice part about them is they are available and they have a high-level API. So we will not have a lot of trouble coding our mocks. Sadly, we lose control, and we lose replicability because between our applications and the hardware, there are a lot of layers of abstractions. The system interrupts, and so on and so on. Now, we can go to real hardware and, for example, use something like a Raspberry Pi or Arduino. They are cheap, they are available. They have a high-level API, and they have medium to high control over what we will do, because they are running already near the metal. And then we can go into professional development boards, and that will provide us the most control, but also comes at a price because the API will be super low level and we will have a lot of trouble doing anything, even simple. So I will show you now two solutions. The first one is actually a funny one, because you can take a Raspberry Pi. I have one with me, it's here. And you can use a very nice library that is called Bleno. That runs on itself. It's a Node module, so you can run it on top of a Raspberry Pi, which makes this complete, like this set special is that Raspberry Pi 3 already has a built-in Bluetooth Low Energy radio, and that makes him some kind of a champion when it comes to connectivity right now. And like, it's easy to use on one side, and it has all the hardware that is necessary. So, like short summary, we will need a Raspberry Pi 3. We will need a power adapter. And I would advise you to use this official Raspberry Pi adapter, because the Raspberry takes a lot of power, so a lot of power. Otherwise, you will get into like fancy situations like random resets and stuff. You will need a Wi-Fi or Ethernet connection to actually get to the Raspberry Pi. And then you would need a software distribution, a Node.js, Bleno, and one code editor. So, again, demo time. One moment. I will just show you how this works when you try to use it. So, Bleno, as said, is a Node.js framework. It has a very nice, simple API. You define yourself a characteristic. You define callbacks for reading and writing. As Bluetooth Low Energy doesn't have any kind of data modeling for like actual values, you need to take care of putting data into raw bytes, so into this buffer. Then you create yourself a service. Again, pretty simple, because it has a UID and a this light characteristic. And then you create yourself actually, you don't create yourself a device. It's Bleno has one on it, so you need to actually handle powering up and situations like advertising and connection and disconnection. So let me show it to you. Now I need to do a little bit juggling with with connections. I didn't want to be dependent on this Wi-Fi, so I'm using my iPad as a hotspot. Short. Yeah, demo mode. So it's enough to run this. So index.js, and we have a running mock. So if I go here, it's actually detected this labs one, so my Raspberry Pi. I can connect to it, which will display it here, down here, and I can actually write a value to it. So, mocking hardware. I actually used Bluetooth Low Energy to connect to it. I estimate it took me something like 20 minutes to set up this whole thing, and that's actually my preferred way to do it right now. If you don't need a lot of control over what you are over this device. So, going back. Now, this is of course not ideal. For example, if you read the documentation for the Bleno library, you will notice that it's really hard to change the name of the Bluetooth Low Energy device. It's also somehow limited in the ways that you can set the connection interval and all kinds of small settings that Bluetooth Low Energy provide. So there is a second solution, my second favorite one. That is, Nordic Semiconductor has a series of chips. This is called the 51 and the 52 series. These are small ARM system on a chips that have a Bluetooth Low Energy radio installed. If you look around, and I look a lot around, and we try to find out which devices have what enabled, you will find out that I estimate something like half of all the IoT devices currently have an NRF chip inside. So, interesting thing, Intel Curie, so this system on a chip from Intel, has one ARM core installed, and that's actually this. So they installed this into their module so that they can have a Bluetooth Low Energy radio. ST-mode beacons. I think most of you heard about ST-mode beacons. They are running on NRF, and so on and so on. Nordic Semiconductor provides boards for them. These are like they look like this. They cost below 50 euros, I think, currently, so they're not super expensive. They're easily available, and yeah, the only thing that you need to do to work with this is a micro USB cable. So for the second demo, we will need this hardware and the tool chain to actually build and compile the application. And here comes the problem. You write in C or in C++. You write against a low-level API that sometimes manipulates raw registers in this ARM chip. It's not really high-level. It's ugly when you are used to something like Bleno, which abstracts everything away. Toolchain setup isn't also very nice. So I would say if you want to do this, you need to be ready that you will spend a lot of time fighting with the code. But yeah, I think I will just show you, and then you can judge for yourself. Okay, so I tend to write my low-level code in C Lion. They have decent support for C and C++. And I have wrote myself a C++ wrapper around the Nordic Semiconductor SDK. This provides me a pretty nice mid-level API, which is pretty declarative. So we create ourselves a bulb service, again. Then we create ourselves a characteristic. We get access to a LED. And then we need to bind everything together. But that would basically be it. Now you can ask myself, hey, but you said it's hard. It is, because if you don't have access to this wrapper, you need to actually go a little bit further, like a lot of abstraction levels lower, and yeah, and one here. And then you have actually, you will see this code that is from the SDK. So for example, this little chunk of code, which sets the access parameters for the device. It's actually a plain old sysstruct that holds Boolean values for different kinds of stuff. Then you have something you need to manually set the buffer for the values. You actually need to allocate memory for it and keep track of it. So I would strongly advise you to use abstraction layer to make this work, but yeah. So this set, let's try to run it. So it's here. It's compiling. Takes a long time. It's programming the board, and we are done. So now, if we go back to the application, now we have this second mock in here. So, and this is called a bulb. And if you look at it, there is a LED in here, and I change the volume, which should actually change the state. So now we have a mock, a device mock, that runs against a true embedded chip that actually gets into hardware. Like true manufacturers put it into hardware. And that's, again, a side effect of this idea of mocking, that if we are lucky and our manufacturer uses the board that we are using, we can even simulate like really nicely the end solution. The only thing that is different is the firmware running on this device, but all other components are okay. What we can also do is, for example, take the firmware that the manufacturer does and put it onto the board to actually check if this other board or this bulb, for example, is done properly from a hardware perspective, because maybe they have a hardware bug. If we run their code on a board that is verified, we can cross out different places where something can go wrong. Okay. So, I hope you liked it. That's something, like the whole idea is something that we used for the first time some 3 years ago. And all the delays that I mentioned and all the situations that I mentioned were actually true. We got the first prototype was supposed to arrive in 1 week. It arrived after 2 months. It turned out it wasn't really ready. It doesn't. The whole Bluetooth low energy communication didn't work yet. Fun part is, in the end, the guys from the company said they saw our mock and said, this code is actually good. Could you put it into the final firmware? And that's something that we actually did. We put code that we wrote in the idea form of mocking into actual production. So, of course, we refactored and took care of it, but it worked. 4 final tips. Always abstract and wrap system interfaces because they are messy and you need to get rid of them. Secondly, mock at the lowest level possible. If you are still mocking on the app side, it will help you. Choose the right hardware for the job. If you want to do a quick mock, choose something that is easy to use. If you want to have a correct, like perfect simulation of the final thing, choose something that is, even from the chip level, on the chip level, the same. And I would say don't fear the bare metal thing. So yeah, it's still programming. It's a different kind of programming, and I would even say it's enjoyable if you come from a completely different place. So it's actually a nice adventure. Just be careful not to stay there because, yeah, then you will curse my name. So that's actually it. Thank you. I hope you liked it. Do you have any questions? No? Okay.
I have a question about the communication. You showed us Raspberry, which communicates with phone, and I think that the communication was with 20
Sorry?
That communication was with IoT commands,
Mm-hmm.
and you showed us hardware
Mm-hmm.
some code with C++ with C. Is that communication the same way?
Yes, it's like both solutions use brutal low energy, basically with a different interface because it was running on a different hardware, but it was still communicating using the standard like GATT, so generic access profile.
So we're emulating whole hardware.
Sorry?
We're emulating whole hardware with that one, right?
With base protocol mocks, yes.
What about security?
Of course you can do that. It's actually better to simulate or actually use an actual device where you can where you can simulate the security on a like real hardware because it will implement the same security features like the true thing.
So it should be at the hardware level, right?
Yes, yes, of course. Yeah, like brutal low energy and a lot of these protocols tend to be somehow complex, so that the applications that build on top of them can be simple. And mocking as a complex system is, I would say, really hard because there are a lot of things that are not described in the specification, and even if it's defined in the specification, it will have something like, for example, 400 sites of documentation how it should work. And then different manufacturers will do it differently. So, of course, you can mock on the upside, so on the base protocol side, but then it will be hard to mock really, because you can then say, does the system make it secure, because that's basically it from your side, and you can say yes, it is secure, and you will not actually test it. When you move to the device side, then you actually get the full thing, because you will actually call the API for the security part on the device also. Okay. Thank you. Neo?
As I understood correctly, you showed us that you have written some abstraction layer in C for this C-based mock.
Yes.
Have you thought about open sourcing it?
Yes, I did. It is not yet there. Sadly, it's a lot of code, and I need some time to finish it. But you can expect in the coming, let's say, month, that it will be available on our Polydia GitHub. Any other questions? Then thank you very much. I hope you enjoy it, and sorry for the delay in the beginning. Happens. Thank you.